everyone, and welcome. So, if you've ever made the jump from basic geometry to trigonometry, you've probably run into this one kind of weird idea: negative angles. I mean, how can a measurement of space be negative? Let's dive in and get this all straightened out.
And that's a totally fair question. Back in geometry class, an angle is just the physical space between two lines, right? You can't have -5 inches of something, so how on earth can you have a -45-degree angle inside a triangle? It just feels wrong. So what's the deal here?
Well, here's the big shift in thinking we need to make. We're not measuring a static thing anymore. In trigonometry, when we're on that big Cartesian grid, an angle isn't a measurement of space, it's an instruction. It's a command that tells us how to move. And this is the whole secret, right here. The minus sign isn't telling you the angle has less than 0 space or anything like that. It's just a simple instruction for direction. Think of it this way. All angles start from the same place, the positive x-axis, pointing to the right. The sign, positive or negative, just tells us which way to turn from there.
This whole new way of looking at angles, it all boils down to two incredibly simple and totally consistent rules. Let's break them down.
Okay, first up, positive angles. If you see a positive angle, like say plus 30 degrees, you're going to rotate counterclockwise. The opposite way a clock's hands move. You start on that x-axis and you swing up right into quadrant I. That's it. Positive means up.
And for negative angles? Well, you just do the exact opposite. You rotate clockwise, just like the hands on a real clock. You start at that same spot on the x-axis, but this time you swing down into quadrant 4. That's the entire secret. Positive is counterclockwise, negative is clockwise. Up versus down.
All right, theory's great and all, but let's actually see how this plays out with a couple of examples. It's time to put these two simple rules into practice.
So let's start with a nice, simple one. We've got an angle of -60 degrees. The question is, where does it stop? Which quadrant does its terminal side land in?
Okay, let's just walk through the logic here. Step 1, we always start on the positive x-axis, pointing right. Step 2, we see that negative sign. That's our command. It means rotate clockwise, so we're heading down. And third, we look at the number itself, 60. Now, a full quadrant is 90 degrees. Since we're only moving 60 degrees, we don't even have enough juice to leave the very first quadrant we enter.
And since we went down from the start, but not far enough to cross the y-axis, our angle of -60 degrees lands squarely in quadrant 4. Simple as that.
All right, let's kick it up a notch. What about -200 degrees? This time the number is bigger than 90, so right away we know we're going to be crossing some quadrant boundaries on this journey.
To keep track, let's just map out the path as we go clockwise. We start at 0. The first 90-degree turn down gets us to -90, pointing straight south. Another 90 degrees of rotation gets us to -180, pointing west. And if we kept going, another 90 would take us to -270, pointing straight up.
So where does our angle -200 fit into all this? Well, it's definitely more rotation than -180, so we know we've swung past that line pointing to the left. But it's not as much as -270. It lands somewhere in that zone between them.
And what do we call that region? The one past -180, but before -270? That's quadrant 2. So an angle of -200 degrees actually ends up in the top left quadrant.
Now that we're getting the hang of this, we've got to talk about a really common mistake. It's a mental trap that so many people fall into when they first see these negative angles.
This is exactly what happens. You're working on a problem and an answer pops out as like -45 degrees. And your first reaction is probably panic, right? You think, wait a minute, that's impossible. The math must be wrong. But you have to remember that core idea we talked about. That minus sign has absolutely nothing to do with the physical size of the angle. It's just a little flag, a directional instruction that says, hey, rotate this way, not that way.
So let's bust this myth for good. The wrong way to think about it is that a negative angle means negative space. That's not it at all. The correct way is this. The sign tells you the direction of rotation, and the number itself, the absolute value, tells you the magnitude, how far to rotate. A -45-degree rotation still sweeps out a 45-degree geometric space.
You might still be thinking, okay, this is a kind of cool math trick, but who actually uses this? Well, it turns out it's used all the time in any system that needs to understand direction in a really efficient way.
For a perfect example, just think about a modern car's steering wheel. The car's computer needs to know not just how much you've turned the wheel, but which way you've turned it. So it sets straight ahead as 0 degrees.
Now look how elegant this system is. When you turn the wheel to the left, that's a counterclockwise motion, right? The computer reads that as a positive angle. It knows positive means left. And when you turn the wheel to the right, that's a clockwise motion, which it reads as a negative angle. It knows negative means right. That plus or minus sign is just a super simple, super powerful flag for direction.
And that's really the bottom line here. Whether it's steering a car, programming a robot arm, or navigating a plane, that little negative sign on an angle isn't some weird impossible number. It's an incredibly useful and efficient command that simply means, go this way.
So, we've pretty much nailed down the whole direction thing. But that brings up a really interesting new question. We know that rotating negative 60 degrees lands you in a certain spot. But how does that direction of rotation affect the actual trig values, like the sine or the cosine? For instance, how does the cosine of negative 60 compare to the cosine of positive 60? It turns out one of them will be the same, and one of them will flip its sign. Exploring why? Well, that's the next step on our journey into trig.